So welcome to the second lecture of Basics of Power Plant Engineering. And this week we are going to start a little bit more talk about steam power plants. So last week we were covering mostly introduction to thermodynamics. And now we are, sorry, this is not moving. Now we're getting ahead. Okay. So now we are getting started with the actual power plants. And before we get to the real power plants, first, we're going to a little bit talk more about this ideal Rankine cycle. What is its thermal efficiency, how we define it, how we can, in different ways, improve it. And in this case, we are still talking more from the perspective of thermodynamics, in the sense that we are talking about an ideal process with isentropic expansion and compression and no pressure drops anywhere, and so on and so forth. Second part is going to be about a little bit introduction to steam power plant process calculations. And then in the final third part, we're going to look at the different performance indicators that we have for steam power plants. How do we calculate them? What do they mean? How are they defined? And without any further ado, we can get started with this first part about thermal efficiency and ways to improve it. So here we have a picture of the simplest possible steam power plant, or the kind of configuration that is behind our ideal Rankine cycle. And the thermal efficiency at the TH is defined as the net power output divided by the heat rate that we put into the process. Or just as well, we might define it as the specific net work per kilogram of work fluid divided by the specific heat energy we put in per kilogram of work fluid. And the net work, what does that mean? That means the work done in the turbine minus the work that the pump has to do. So in the turbine, the fluid does work, and in the pump, of course, the pump does work into the fluid. And we can define this specific net works in both of those components as just simply the enthalpy change, specific enthalpy change over each of the components. So for the turbine, H1 minus H2, and for the pump, H4 minus H3. And the heat input, similarly, it's the enthalpy change over the boiler or heat exchanger component. And then the equation becomes very simple. So it's just the enthalpy difference, the difference between the enthalpy differences over the components. And that is the thermal efficiency, or we also call it process efficiency. So those two mean the exact same thing. Important thing to remember is that we are talking about specifically the heat input to the work fluid. So for example, if we're talking about actual power plants, it's not the fuel input to the boiler, because only part of that we can get into the work fluid. And with those components, we're talking about the work that the fluid does in the component, in the turbine, or the work that the pump does into the fluid. So we're not talking about what we get out of the power plant as generator power, for example. But for now, we are still looking at these ideal processes where we don't care about generators or boilers. They don't exist. We are just looking at the process, and even that one is an ideal one with lossless components, basically. Now, that was how it was defined with the works. And now we remember that from last week's lecture, that the TS diagram is supposed to be quite helpful for us in understanding the efficiencies of different thermodynamic cycles. And in this case, we can get started with the Rankine cycle. It's drawn here as a process in the water vapor TS chart. And looking at this, if we think about how the efficiency looks like if we define it through the heat inputs and heat outputs. So we remember that the heat basically is integral from beginning point to the end point TDS. So basically that means that if we are right here in this corner, we're at the point where heat input in the boiler begins. And then we start to heat the work fluid until we get to the point where the curve actually meets the saturated liquid water curve. So it looks like we are going on the curve. And this is just because all the changes in liquid form show very, very tiny little temperature variations here. But basically, we are not on the saturated curve until we hit it right here. Then we start boiling, constant temperature process until every bit of water has been boiled into water. We are here in saturated liquid, saturated vapor, and then we do the superheat. Everything that is underneath this curve is graphically depicted in this diagram as heat. And then heat removal, same thing. This is the point 2 at turbine exhaust and condenser inlet. We start removing heat, so we move from right to left, and everything is underneath is removed heat. And work is then what is in between, because we have no other losses here in an ideal process. So basically, specific net work is heat in minus heat out. And in this form of the definition of the thermal efficiency, we can divide it with Q in, and our efficiency looks like 1 minus the ratio of heats. Now, because I mentioned that this definition of heat being TDS, sorry, but this is, by the way, this should be dQ is TDS. Q is integral over TDS. So basically, what this means is that we can define the efficiency as 1 minus the ratio of temperatures. So temperature 0.2, condenser temperature, which is saturation temperature according to the pressure there, divided by the mean temperature of heat addition. So what this form of the definition of thermal equation tells us is basically that we can always improve efficiency if we can increase the heat addition temperature, or we can decrease the heat removal temperature. And basically, of all of these ways that we are now going to start looking at how we can improve the efficiency of an ideal Rankine cycle, we're going to be basically focusing on how to increase the average temperature of heat addition, or how to decrease the average temperature of heat removal. And first thing that we could think of doing is we could try to increase the live steam pressure. And what does that do? So if we move from 5 megapascals to 16 megapascals of pressure, the TS diagram process looks like this now. And quite clearly we can see that the average temperature of heat addition is increased, mostly because the boiling temperature is now increased because of the higher pressure. So heat addition in this part goes up. And heat removal temperature doesn't change anywhere because we didn't change anything except the live steam pressure. What we also notice is that the net work shape basically changes, but the area itself doesn't change very much. So green bit is what we gain, red bit is what we lose. You win some, lose some, it's all the same in the end. So not much of a change, but we have a clear reduction in the heat removal. So if we get the same amount of work, but we have to remove less heat, clearly that's going to be improvement of efficiency. One drawback, if we a little bit look into the real power plant side of things from the point of view of this ideal cycle, is that if we improve or increase the live steam pressure, what it means that we are going to be diving deeper into the wet steam area. And what that means is that there's going to be more water droplets in the steam as it comes out of the turbine. And that can not necessarily always be a good thing. So if we have too much water droplets in the steam, it's going to be doing bad things to the turbine exhaust final stages, where the turbine blades are going to get bombarded with water droplets. So typically in most cases, we don't want to go deeper than 86, 88% of vapor fraction or steam quality in the exhaust steam. It's not an absolute limit. You can go deeper, but then either your turbine blades are not going to survive that long, or you're going to have to pay extra to get the sort of materials that will survive a little bit better. So usually we don't want to get much deeper than something like 87%. But that's not really what we are focusing yet on this lecture, at this part at least, so nothing more about that. So this is how live steam pressure can be used to increase the mean temperature of heat addition. Of course, the other obvious way to increase it is to simply increase the live steam temperature. So continuing from where we were in the previous version of the cycle, we add more temperature. Again, clear impact is going to be that mean temperature of heat addition goes up, and still the heat removal temperature remains constant. Basically, all of the area inside is addition of specific net work, and there is no red area that will indicate that there was any bit of the process that we lost as net work. So we get more work out of same mass flow rate of work fluid. And because we are moving now back to the right, we are removing a little bit more heat. But clearly, this process that we added is operating at a higher efficiency than the bit of the process that was there before, because basically the ratio of the work to removed heat is now much more favorable. So net effect is that efficiency of the process is going to be increased. And the additional benefit was that because we're again moving to the right side, we are getting towards less moisture at the turbine exhaust. Then the other thing that we can do to this Rankine process is, instead of trying to increase the average temperature of heat addition, we can try to reduce the temperature of heat removal. And basically what that means is reducing the condenser pressure, because when pressure goes down, the boiling point, the saturation temperature also goes down. So process changes like this. And now how the areas change, well, there was one very obvious change, but there's some few a little bit less obvious ones. One is that we are adding a little bit more heat, and we do this heat addition at a very unfavorable temperature. Luckily, it's only a very minuscule part of the whole heat addition. So our mean temperature of heat addition goes down, which is a bad thing, but it goes down only very little, so it doesn't matter much. Heat removal. There's a bit of the process that heat removal increases, and there's the other bit of the process where the heat removal decreases. So basically, this light gray bit, where we manage to reduce the amount of heat removal, is bigger than this additional heat that we have to remove, which is the black bar here. So that seems to indicate that something favorable is happening. And what happens to the whole process and the specific net work, the area that is inside of this curve, it's very, very similar to this light gray. So basically, just this tiny little bit of the corner triangle here, we also get this additional work. Net outcome basically looks like we are getting more net work, and we are removing slightly less heat from the process. So clearly it looks like this is going to be something where we're going to improve the efficiency. So basically our mean temperature of heat addition goes down just a tiny bit, and our mean temperature of heat removal goes down clearly more. So net effect is beneficial. And the drawback is that because we are again going deeper into this wet steam area, it means that we're going to have more moisture at the exhaust. Well, these were the things that we can do to the basic ideal Rankine cycle without doing any modifications other than process parameters to it. But we can also modify the process itself a little bit more. And one of the ways how we can do it is to add something called reheat. So reheat means basically that instead of expanding the steam in the turbine all the way nonstop from live steam temperature to the condenser saturated temperature, we expand it first only a little bit and then reheat it in the boiler. So it looks something like this. What that means, what we can do, and what we aim to do with this is to increase the mean temperature of heat addition. Now, the important thing to notice is that it's not guaranteed that no matter how we do it, we're going to increase the mean temperature. Here, the way that it is depicted, clearly we are increasing the mean temperature of heat addition. But if we were to, for example, expand the steam all the way to 200 kilopascals or even deeper, and then start adding more heat, that would not increase the temperature of heat addition. So with reheat, it's important to do it at a high enough pressure. And clearly the area inside of the thermodynamic cycle increases, so it means that the specific work out of the work fluid per kilogram is going to be increased. And condenser pressure is still unchanged, so heat removal temperature, nothing happens. And when you do it right, this means that efficiency goes up in addition to work going up. And also because we are moving right, that means that less moisture at turbine exhaust. And this is how the process would look like. So basically, if there is reheat in the power plant, it means that we are basically separating the turbine into at least two different bits. So first, high pressure turbine expand a little bit, sends the steam back to superheater, and then the final expansion in the low pressure turbine. The other thing that we can do is add something called feedwater preheating with bleed steam or extraction steam. So I'm using those terms pretty much interchangeably. They mean almost exactly the same thing. It means that we are taking steam out of the turbine. We take some of the steam out from the turbine before it expands all the way to the condenser pressure. So there's a slight difference between the terms. Bleed usually implies that if, for example, the conditions in the turbine change, the steam comes out in whatever state it happens to come out. If pressures change in turbine, then exhaust pressure also changes. Extraction is sometimes means that you try to control the extraction pressure. That can be done in various ways, but within this course, basically, if we see bleed steam or extraction steam, you can safely assume that it means the same thing. It means that you're taking a little bit of steam out of the turbine before it fully expands. And feedwater preheating with this kind of steam, it could look, for example, like this. So here we have, and by the way, there are some of these labels in the figures throughout this course. They might seem strange to the English-speaking ones. So they are based in the Finnish language. K here, for example, it comes from kattila. In Finnish means boiler, and VO. And so a lot of figures that are basically based on some old Finnish courses. I haven't had time to change all of them. So VO means väliotto, means extraction or bleed point from the turbine. And what we do with this, so basically now we are adding steam into the feedwater, and we notice that we have now two pumps, not one. So we have the condensate pump to get the feed to a little bit pressure, then we mix steam with it. Presumably, we're going to have a little bit hotter water at this point, and then that water we fully pressurize before putting it into the boiler. What that's going to happen is that mean temperature of heat addition is going to go up. It's going to go up because although the same temperature changes happen throughout here to get to this point as in the previous version, now all of the heating up to this point happens without any heat addition from outside into the process. So heating it up to 0.5 is just the internal process within the process itself. So if we look at how it looks like in the TS chart, the point BO would be here already just tiny little bit on the wet steam side. And the rest of the steam expands fully to 0.2, condenses in the turbine. Here is zoomed up to show what happens in the condensate pump. And then by mixing these two streams here, we get to the 0.5. So we have the steam from the extraction point coming from the right to 0.5, and then we have the liquid condensate at 200 kilopascals coming from here, and they meet on the saturated liquid line where they become mixed and then are pumped up to pressure. What this means is basically that there is no heat input. So this area is heat input to the liquid stream, but from within the process. No heat input to the process. The other thing that what this means is that because we are now splitting the mass flow rates, so basically with these kinds of processes where we have actually some bleed steam or extraction steam feed water heating going on, basically we have different mass flow rates at different parts of the process. And that means that the areas are no longer really fully comparable because some of the areas are taking place with the smaller or larger mass flow rate. But we can still see that the point where heat addition to the process begins is now at a higher temperature. So that should improve our process efficiency. And then that was what was so-called open feedwater heater. So that was the de-aerator or feedwater tank. But we can also have more stages of feedwater preheating, and then we add so-called closed feed heaters or surface heaters. So in Finnish, we usually call this pinta-esilämmet, and literally translates to surface heater. That's more descriptive term, but in English, unfortunately, the more common terms are open and closed feed heaters. So those are the terms that we're going to be using mostly during this course. It's important to understand what they mean. So this open feed heater is basically just a tank where steam and water mix, and they exit at the saturated liquid conditions. The closed feed heater, surface heater, is basically a heat exchanger. There's no mixing. The steam just releases heat to warm up the water. And basically, the construction is always the same. They are U-tube, shell and tube condensers. In the later lectures, we're going to look a little bit more how they actually look like from the inside, how they are constructed. But for now, just enough to know that they are heat exchangers and the two streams do not become mixed. Water is in the tubes always, and the steam is always on the shell side, condensing on the outside surface of those tubes. So there are many, many very small tubes on the surface of which the steam is condensing. Sometimes we might want to intentionally subcool the condensate. So this is typically happening, especially in this so-called high pressure preheaters. High pressure preheaters are the ones that are after the feed water pump. And we are usually directing the condensate that comes out of the steam from high pressure ones after feed water pump. We can dump it to the feed water tank or de-aerator. And then if we would have low pressure preheaters here, we could just dump the condensate to the condenser. We call these secondary condensates, these ones that come from, for example, extraction steam condensing in a surface heater. And main condensate is the condensate that is coming out of the condenser. And yeah, as I said, we talk about high pressure and low pressure preheaters, and definition is if the feed heater is going to be after the feed water pump, it's going to be operating in very high pressure, and that has a significant impact on how it has to be constructed. We will see that on the next lecture. And then if it's before the feed water tank, it's going to be at much lower pressure, very much lighter construction, and we call those low pressure preheaters. So if you have separate high pressure turbine, low pressure turbine, whether you take the steam from which of those two turbines has no impact on, if you call it, high pressure or low pressure feed heater. And it is quite common that the last low pressure feed heaters right before the feed water tank, they very often may take steam from the last extractions of the high pressure turbine if you have one. Now, one thing about feed water preheating with bleed steam. So our aim was to improve the process efficiency. And when we do this, that aim is going to be met. We don't have to wonder about the efficiencies going up only if some condition is met. If you add feed water heating, that is going to improve the process efficiency. The important thing to understand is that it doesn't necessarily always translate to improving the power plant efficiency. So for that purpose, I've drawn here a picture of the boiler, what happens here. So normally if you put feed water in the boiler, you can heat it to a pretty hot temperature, and it goes into the boiler in what is called the Economizer. So that's the feed water preheater that gets the water very close, not quite at boiling point temperature, but very close before putting it into this so-called drum. Now in a normal boiler, you would have as the very last heat exchanger surface, so hot flue gases go here, they're cooling, 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 and then the last heat exchanger surface in the back pass that they meet is the air preheater. And with the cold air going into the boiler, we can always cool the flue gases pretty much as cold as we want in most boilers, but there are a couple of exceptions. So some recovery boilers, we are going to talk about that later in this course, and also in so-called heat recovery steam generators in combined cycle power plants. For various reasons, you might not actually have this air preheater then. And in these cases, if you add more feed heaters here and you get very hot temperature of your feed water, yes, the process efficiency of the steam cycle is going to go up. But that's going to come at a cost of putting hotter and hotter flue gases into the air, and boiler efficiency is going to go down, and that's not going to be helpful for the whole power plant efficiency. So that is something to keep in mind, that the ultimate final goal that we're looking at is improving the power plant efficiency. And that was pretty much the contents of the first part. So now we covered what we can do to improve the thermal process efficiency of the steam cycle in an ideal Rankine cycle, how we can modify the process parameters, how we can modify the process itself. And now in the following parts of this lecture and the whole course pretty much, we're going to look at what happens then in a real power plant where we actually have losses. So we have pressure drops, we have heat losses to the environment, we have irreversibilities in turbines and pumps. In a heat exchanger, there are always irreversibilities. Basically, heat transfer requires temperature difference, and transferring heat over temperature difference inherently always increases entropy and creates irreversibility there. We have mechanical losses, we have various blow dance leakages, work fluid losses in a way from the process. And we have a whole bunch of different types of auxiliary equipment that needs electricity or high pressure steam to run, and they have their consumptions. So basically the next parts of the lecture are going to describe the calculation process of real power plants. We'll start with a little bit of introduction, process calculations, and then we're going to look at the basic common performance indicators for the whole power plant and different parts in it, so that we can take into account all of these things that happen in the real power plants. But that basically concludes the first part of the lecture.